and kind of how they dissociate in water, how there's this kind of back and forth happening with the acids and bases dissociated and forming hydronium ion. We talked about naming the acids, and then we looked at conjugate acids and bases, and we practiced a little bit about how to find a conjugate acid or a conjugate base of a molecule. So hopefully you've been practicing that so you can fill in these kinds of tables. We'll have a quiz on Thursday. We'll do another quiz next Thursday on the acids and bases stuff. So please be working on that because we'll be done with that shortly. Okay, we talked a little bit about strength and pH, this kind of pH scale, and that's where we stopped. So we talked about how we can figure out the pH from the hydronium ion concentration by taking a negative log. And we can either do that in our heads if it's just an easy number like 10 to the minus 7, and we just take the little exponent and say that's a pH of 7. If it's a more complicated number, we can plug it into our calculator and use the log key to tell us the pH that way. So we'll practice that a little bit today. Just to remind ourselves of the pH scale, generally 0 to 14. We talk about a pH of 7 as being neutral, but really kind of in that range is neutral. So 6 to 8, something like that, we would say is really neutral pH. One thing we didn't get a chance to do last week before we ran out of time was to annotate this scale a little bit. So some of the things that you might encounter. Right about here, this is our physiological or our blood pH. Blood has to be a very precise pH all the time, between 7.35 and 7.45. Any real deviation from that, you start having some big problems. Chemical reactions don't work properly, cells start dying, all of that. So one thing we'll talk about today in a little bit is something called buffers, which is how your blood controls its pH. This has been kind of misunderstood a little bit in that I think we mentioned this last week too, but there's a lot of products out there that talk about balancing your body's pH. Have you seen that sort of thing? I mean, that's pretty much all nonsense. I know I think we mentioned that before. Your blood does have to control its pH in a very small range, but what you eat does not really affect that. What you drink does not really affect that. So your blood does that based on carbon dioxide. Actually, it's breathing that controls your blood pH. So let's look at a couple other things. Over on the acidic side of the spectrum, I've got my delicious, healthy drink here. That comes in about here. Coke has a pH of 3, so very acidic. All that phosphoric acid and carbonic acid. That's why it's so bad for your teeth. You can actually remove rust with it. Clean up metal, nice. Corroded metal will clean up nicely with Coke on account of that. So that's how you know it's healthy. Anything that takes the rust off of metal, it's got to be a good thing to eat, right? Other things, just below that is your stomach acid. The fluid in your stomach is predominantly hydrochloric acid, and it stays about a pH of 2. And that's how it helps break down your food. And then over on the other end of the spectrum, basic stuff is like cleaning agents, ammonia, bleach, that kind of stuff is going to have pH in the like 10, 12 range, something like that. We don't tend to eat a lot of stuff that's basic, maybe some baking soda. Cranberry juice is moderately basic. Most of the time when we encounter basic stuff, it's cleaning agents. And we talked last time about how basic or bases can be just as corrosive, just as dangerous as acids, depending on their concentration and what they can do. But these really strong cleaning agents, oven cleaner is a base, has a pH of pretty close to 14. So those kinds of things are just as dangerous. We also mentioned how, and this will be important with what we talk about in a minute, acid-base strength remember that when we talk about strength, strong acids versus weak acids, we're not talking about how corrosive or how dangerous it is. We're talking about how much it dissociates or breaks apart or forms ions in water. A strong acid like HCl will form a lot of hydronium in water, and there won't really be any whole HCl molecules left. A weak acid like HF will mostly stay together and just form a little bit of hydronium ions. So that's what makes a strong acid versus a weak acid. It has nothing to do with how dangerous it is or how corrosive it is. All right, so let's look at calculating some of these things. As we saw, oops, we'll go back up to that equation. As we saw up here, pure water can actually partially dissociate itself and form hydronium and hydroxide. And it forms enough to have exactly or about 10 to the minus 7th molar concentration. And actually that's of each. So one thing I didn't want to confuse you, but the concentration of hydroxide, which remember these little brackets around it mean concentration, is also 10 to the minus 7th molar in pure water. So you've got an equal, for every hydronium ion you form, you got to form a hydroxide ion too in pure water. So the pH scale really just describes the offset here. As you have more hydronium, you have to have less hydroxide. We call that acidic. As you have less hydronium, you have more hydroxide. We call that basic. So the way that we express that, we can express that in two different ways. One is to say the pH plus the pOH equals 14. Now the pOH is exactly the same thing, but with the hydroxide ion concentration. So the pOH is the negative log of the hydroxide ion concentration. Just like the pH was the negative log of the hydronium concentration. And as we said, those two things are related. So if you know the pH, you can also find the hydronium ion concentration. If you know the hydroxide ion concentration, you can find the pH, and you can keep going back and forth using these methods. So for instance, let's look at an example problem. If the hydroxide ion concentration is 10 to the minus 5th molar, what is the hydronium ion concentration? We can answer this based on that equation above. We can find the pH, we can solve for the OH, or the pOH, and then find the hydronium ion concentration. So if the OH concentration, the hydroxide ion concentration is 10 to the minus 5th molar, then the pOH is going to be the negative log of that. So what's the negative log of 10 to the minus 5? Right, that just tells us the exponent, so that's 5. So in this case, the pOH is 5. So then we can use that equation above to solve for the pH. The pH plus 5 equals 14. So that means that the pH has to be 9. Okay. The question doesn't ask us for the pH, though. It asks us for the hydronium ion concentration. So if we have a pH, how do we find a hydronium concentration? In other words, we have this kind of a situation. The negative log of something, of the hydronium concentration, equals 9. So how do we undo a log? You know? What's an unlog? Right. If the log tells us the exponent of a 10 to the power of something, then the unlog is to take the 10 to that particular power. So if the negative log of the hydronium ion is 9, then the hydronium ion concentration must be 10 to the minus 9. See, so you just take that little number, that 9, and you stick it back up on that 10. And that's how you go back and forth between log. Now, if that were a not nice number, like let's say it was 9.2 or something. So then we would have 10 to the minus 9.2. But we don't usually leave things in that form. So we would put that in our calculator and say, okay, what's 10 to the minus 9.2? And then we'd write down that answer as our answer. All right, so let's try that going the other way. If the pH is, let's say, 3.2, what is the hydroxide ion concentration? So pH 3.2, what's the hydroxide ion concentration? So first we have to find the pOH, and then we find the concentration from there by undoing it in the same way. So you've got to remember that 14 number. The pH and the pOH have to add up to 14. So in this case, 3.2 plus the pOH has to equal 14. So then the pOH has to equal, what is that? 10.8, right? 14 minus 3.2 is 10.8. All right, so if that's our pOH, then again, we can undo that using that power of 10 to find the hydroxide ion concentration. Hydroxide ion concentration is going to be 10 to the minus 10.8. We stick that number right up there on that 10. And that's a weird kind of thing to have. So we're going to break that down a little bit and calculate that. So we've got, in this calculator, you got to do the 10.8 first, and then the minus, and then 10 to that. And that little e over here means times 10 to the. So that tells us it's 1.5. That's a lot of digits. We don't need that many digits. We'll say 1.6 times 10 to the minus 11 molar. That's what the calculator tells us. All right, so we can find the hydroxide or hydronium ion concentrations depending on which one we have. We can find the other one using this idea that they have to add up to 14. Okay. What's next? So the next thing we want to talk about is buffers. Buffers are solutions that prevent wide fluctuations in pH. So it stops the pH from going around crazy. It's really important, especially in things like our blood, and things like food, in science things, in stuff like you're going to put some solution into your eye. You want it to be buffered so it's the right pH for your eye. All these kinds of things. If you have a problem with heartburn or those kinds of issues, you might want to use something that has more of a buffering capacity to basically stop those crazy fluctuations in pH, to control the pH and keep it in a particular range. Let me show you an example of kind of how they work. So let's say first we don't have a buffer. First we just have some water, a little beaker full of water. And you'll have a chance to do this next week in lab. Let's say to that little thing of water, we add a few drops of hydrochloric acid, a few drops of HCl. Just drop it in the water there. We now have water with some HCl in it. It forms its hydronium, does all the stuff we've talked about, the HCl, but we're just talking about a few drops. If that water pH started around 7, this ending pH probably suddenly dropped all the way down to 1. It doesn't take much. Remember, we're talking about tiny concentrations, 10 to the minus 7th molar, 10 to the minus 1 molar. The difference between 10 to the minus 7th molar and 10 to the minus 1 molar is really not that much when you're talking about a drop size. So a few drops and suddenly you've totally changed your pH from neutral to super acidic. Works the same way in the other direction. Instead of a few drops, I'm just going to say a little bit of sodium hydroxide, a strong base, because it's a solid. So you just drop, a little grain of sodium hydroxide in there, or a few drops of a sodium hydroxide solution, and you got the same thing. Now we have water and sodium hydroxide, and our pH has suddenly jumped up to like 13 or 14. Super basic, just from a little bit. So that's normal behavior of a neutral water solution. If we don't want that to happen, or if we have an environment where that pH needs to be controlled, we need to have a buffer. And the way that a buffer works is it still changes the pH, but it allows the pH to change in tiny, tiny increments. So I'm going to redraw this next to it here. And this time we're going to look at a buffer. And this buffer is going to have a pH of 7, just like the water did. Now, a buffer, you can actually control the pH. You can, if you're making a buffer solution, you can put the ingredients in just right to control it to whatever pH you want. If you go on and take chemistry, I think 122 is the class, you'll learn how to do all that and all the calculations to make the proper buffer. Does that sound like fun? I think you should probably take that. It'd be a good time. So let's do the same thing for this. I'll just copy over my arrows here. Magic of technology. We're going to do the same thing. But now that pH is, and I'm just making up numbers here, but whoops, should go the other way. The pH still goes down with a few drops of HCl, but just a tiny amount. And maybe here the pH just goes up a tiny amount. So that's how a buffer works. It controls that pH. Now let's look at what's going on chemically that actually allows that to happen. A buffer uses this idea of the weak base, or a weak acid. A buffer solution is made by mixing a weak acid and its conjugate base. So, for instance, let's take carbonic acid. Carbonic acid is a weak acid, H2CO3. What's the conjugate base of carbonic acid? Remember how to make those? Yeah. So we get rid of H plus to make the conjugate base, and that's going to leave HCO3 minus. Remember, we have to change the charge as well when we take that away, because we're taking away a plus. So you take away a plus from something that's neutral, and you're left with something that's -1. All right, so that's our buffer solution, the weak acid and its conjugate base. You put those two things together, and here's what happens. So let's say we're going to use these kind of bar graphs. They do it this way in the book. So here's our buffer. And we've got, let's say, this much carbonic acid and an equal amount of bicarbonate. This is like a graph. Okay. So we've got an equal amount of each of them, whatever that is. Then we add acid. Now normally, H plus, adding protons, if we just add protons to water, like when we dissolve HCl in water, all those protons go to form hydronium ions, and that changes the pH drastically, because we now have a whole bunch of hydronium that we didn't have before. But if you've got a buffer solution, instead of making hydronium ions, what happens is the H plus actually reacts with the conjugate base. So this stuff goes with this stuff, and you end up with the same amount of carbonic acid, or sorry, you end up with a little bit more. Let me try that again. You end up with a little bit more carbonic acid and a little bit less bicarbonate. So adding the H plus turns bicarbonate back into carbonic acid. And so you change the ratio of bicarbonate to carbonic acid, but because that's a weak acid, that actually doesn't really contribute much to the hydronium in solution. So instead of those H pluses becoming hydronium, which changes the pH, they become H2CO3, which just floats around the solution and doesn't do anything to the pH. So we're adding H plus without changing the pH. And that's the magic of a buffer solution. It also works the other way. So let's see what happens when we add hydroxide. Now, when we add hydroxide to a regular, just a solution of water, we suddenly have a bunch of hydroxide in that water, and that increases the hydroxide concentration, which raises the pH. So decreases the hydronium concentration, raises the pH. But when we add it to the buffer, the hydroxide goes and picks off one of those hydrogens from the H2CO3. So it turns H2CO3 into HCO3 minus. And so all that happens now is we change our ratios of our two buffer parts. So we've got a little less H2CO3 now and a little more bicarbonate, but we haven't really changed the hydronium or hydroxide concentration in solution. So instead of a bunch of hydroxide being in solution, it takes a hydrogen from the H2CO3, becomes water, and doesn't really change the pH. So as you can see, things are kind of being used up here. So there is a limit to a buffering capacity of a solution. If you kept adding more and more H or more and more OH, eventually those bars would go and you'd run out of stuff, and then you'd start changing the pH drastically, so the buffer would break down. But depending on how you build your buffer and how much there is, you've got at least some room there. And that's why it's called a buffer. Like, just like we use that in everyday life, like a buffer zone or something. It gives you some way to control the pH a little bit and stop these huge changes, these huge fluctuations. So in our blood, this is exactly how it works. The reactions that happen in our blood, carbon dioxide from our respiration, carbon dioxide is a waste product that we produce, reacts with water to form carbonic acid. Exactly this buffer that we've been talking about is what's happening in our blood. And this actually goes both ways, because carbonic acid also breaks down to form CO2, but that's how we form a buffer. carbonic acid exists in our bloodstream, and then that carbonic acid reacts further with more water to form bicarbonate and a little bit of hydronium. So there's our two parts from the buffer we just talked about. When our carbon dioxide from our body, from the waste of our respiration, is produced into the bloodstream, it dissolves in the bloodstream and forms H2CO3. That H2CO3 then goes and forms the base, and now we have a buffer. So those molecules exist in our bloodstream to help control that pH and keep it in that 7.35 to 7.45 type range. This also means that having too much or too little CO2 is going to affect the buffering capacity of our blood. So if you have too much CO2 in your blood, what do you think that causes? Is that going to cause your blood to be too acidic or too basic, based on those equations? Too much CO2 is going to be too acidic or too basic?
Acidic.
Acidic. Why? That's right. How do you know?
There is more acid from carbon dioxide.
Yeah, so if there's more carbon dioxide, it's going to form more carbonic acid. If there's more carbonic acid, it's going to form more hydronium, and that's ultimately what controls the pH. So too much CO2 makes it more acidic, which is making the pH too low. And we have a name for that. That's called acidosis. So if your blood gets too acidic, that's called acidosis. And the opposite also can happen. If you have too little CO2, that's going to become too basic, and it's going to go too high of a pH. And that's called alkalosis. So that's what happens if your blood gets too basic. Now, because this is all controlled by your CO2, of course, our bodies, all kinds of stuff can affect this. But one thing that really clearly affects it is actually our breathing. Remember, when you breathe, you take in some air, a little bit of it gets used up in respiration, you blow it out, and when you exhale, you're also getting rid of some of the CO2 that was put off as a waste product. So if you start hyperventilating, you know what that is? When you just like breathe really, really hard and fast. Mm-hmm. If you start hyperventilating, what can happen is you exhale too much CO2. There's not enough CO2 left in your lungs to dissolve in your blood properly. You're just expelling too much CO2. And if you are expelling too much CO2, that means there's not enough CO2 left in your blood, and that makes your blood get too basic, and that puts you in this state of alkalosis. Yeah?
So why they have you breathe into a paper bag so you can get that CO2 back in?
Well, that's the idea, yeah. If you breathe in the paper bag, you're breathing in more of your CO2, and you stop blowing so much of it off. Because if you blow off too much CO2, that changes your blood, right? So that's the paper bag thing. Now, the real answer to that, I think this has been tested, at least I read something about it, that the paper bag is more about giving you something to focus on so that you calm down, and less about the actual chemistry of like the thing. But the book actually uses it as an example because it fits so nicely here. So it might not be totally true, but it works nicely if you think about it that way. But yeah, I think it's actually more about just like, if you're freaking out and hyperventilating and someone says, here, breathe into this bag, then you've got this thing to like focus on and actually do to help yourself. Yeah. Okay, so that's how those things can be affected. All right. The last thing we're going to talk about in this chapter is something that we're going to work on next week in lab, which is called titration. Have you ever heard of a titration? No. Titration is a way of measuring a concentration of acid by using a known concentration of base. So a titration is a carefully controlled neutralization reaction. A neutralization reaction, as we said, was when an acid and a base react together to become neutral. And the one we're going to do next week looks like this. So we will take this compound, which is acetic acid, and we're going to react it with sodium hydroxide, which is the base. Now, when acetic acid and sodium hydroxide react, they neutralize each other. You've got an acid and a base. They neutralize each other and form water. And aqueous sodium acetate. We call it neutralization because you took something that was a strong, or not strong, but there was an acid and something that was a base. You combine them, and now you only have neutral things, water and a salt, sodium acetate. Neutralization reactions between acids and bases are really just double replacement. Remember we talked about double replacement reactions where the things switch? That's exactly what's happening here. The H from the acetic acid is going with the OH from the NaOH and becoming HOH, which is water, H2O. And then the sodium is going with the acetate to make the other pair. So they're just switching partners the same way as the ionic double replacement reactions did. The only difference here is now we're forming water as one of the products. So that's a key to see in a neutralization reaction, that you form water. What we would do in this situation is, let's say we have an unknown. This is what you're going to do next week. You have an unknown concentration of acetic acid. So you have some acetic acid, you don't know how much you have. But let's say you have a sodium hydroxide solution that you've made yourself, so you know exactly the concentration. Let's say that it is 0.1099 molar. Right, so we took a certain amount of sodium hydroxide pellets, dissolved it. We know it's exactly 0.1099 molar. It's been standardized or whatever. Okay. We can do an experiment using that known sodium hydroxide, and we'll do this next week, to figure out how much acetic acid we had and what the concentration of the acetic acid is. So here's what the experiment looks like. Let's say, so you take a flask. Not a great drawing of a flask. It's okay. There's our flask. We should probably send that one back and get a little bit straighter one, but it's all right. What we would do is we'd put in a known amount of acetic acid down in the bottom. So let's say we'd use a pipette or something. We'd be really careful. And we put in exactly 20 milliliters of acetic acid in this flask. And then we put in a few drops of something called an indicator. An indicator is a chemical that changes color based on pH. The one we're going to use is called phenolphthalein. And what that does is when you put it in an acidic solution, it's totally clear, colorless, doesn't look like anything. But as soon as that solution turns basic, it turns pink. So what we can do is we can say, all right, now this indicator's in there. And now we're going to add sodium hydroxide, our known sodium hydroxide, until it turns pink. Because exactly at the point where it turns pink is when all of the acetic acid has been neutralized. So there's going to be more acetic acid. It's going to be acidic until there's just enough sodium hydroxide to react with all the acetic acid, and then suddenly it turns pink. And that, we call that our equivalence point or our end point. And that will tell us exactly how much we need. So we're going to use this device called a burette, which we've seen before. It has this kind of long, skinny tip with a valve coming off of it, and then a scale on the side. And our sodium hydroxide is in there. We're going to add the sodium hydroxide down into the acid and kind of like swirl it around just by hand until the instant it turns pink. And let's say that at that instant it turns pink, let's say 13.23 milliliters of sodium hydroxide are added. You don't have to watch the scale, you just watch the drop by drop, and then it kind of goes in, and all of a sudden you see it turn pink, and you stop it, and then you look at the scale, you subtract where it ended from where it started, and we'll go over how to do that in lab. And you know exactly how much NaOH you added. Now, we know everything we need to know now. We have a volume, because we know how much NaOH we added. We have a concentration, because we know the concentration of the NaOH we started with. So we can figure out how many moles we added of that sodium hydroxide. Remember, that 0.1099 molar means 0.1099 moles per 1 liter. So if we added 13.23 milliliters, we know exactly how many moles we added. Oops. So we have to convert this to liters to do that. So that's 0.1323 liters. Liters cancel. And so that's going to be 0.1099 times 0.01323 is 0.00145 moles of sodium hydroxide added. So exactly at that point where it turned pink, we added 0.00145. If we look back at that equation, sodium hydroxide and acetic acid react in a 1-to-1 ratio. So exactly at that point, that means that there were also 0.00145 moles of acetic acid in the bottom of that flask, because there has to be 1 NaOH for every 1 acetic acid. So if we added exactly that many moles of NaOH, we must have had exactly that many moles of acetic acid to start with. So our original acetic acid must have been 0.00145 moles in 20 milliliters, because we added 20 milliliters to that flask. So now we have a moles and we have volume, so we can find concentration. .0725, 0.07. So that tells us that our initial concentration for that acetic acid solution that was initially unknown, we've now found it, is 0.0725 molar. So we figured out how much NaOH did we add. We calculated the moles of NaOH. We saw that that's got to be the same number as the moles of acetic acid that we started with. And then we made those equivalent and we divided by the volume to get the concentration. So that's how you use a titration to figure out the concentration of an unknown acid or base. You can also do it the other way. You can have an acid that you know the concentration of and titrate with a base and figure out how much of the base you have. This is a very important analytical method. This is still used all over the place. Any high-tech lab, I mean, it looks kind of low-tech with the things that you're doing with the flask, but any big labs, you know, EPA that analyzes water, medical labs that are trying to analyze amounts of certain things are all going to use titrations to do that. Because it's a very powerful technique. You can simply put these things together and figure out exactly how much of one or the other that you have. So we will be doing a titration as part of the acid-base lab next week, so you can kind of get a practice on that and have an idea of how that works. All right, now, I think some of these calculations are a little bit beyond what we're going to do on exams. Let me check that. I could be wrong. But let's pull up Blackboard and check what this section looks like. Okay, so here are the things you need to be able to do about acids and bases. You need to define them. You need to find conjugate acids and bases, know about hydronium ions, strong and weak acids and bases, some examples, some names, ionization of water, pH and POH, which we talked about. Talk about an indicator, litmus paper, which we'll do in lab, and then a buffer. So you notice on that list, it doesn't say calculate amounts from a titration or something like that. So you won't have to do that. But these are the things you should be able to do. And if you look in your book, there's a nice list of homework problems in chapter 10 to practice that. So make sure you go through those before next Thursday when we'll do a quiz. And then there's just 2 sections left. Nuclear chemistry and organic chemistry. We've got, I think, 5 weeks after this one. 1 exam, 1 final, a few more quizzes, and we'll be done. So we're almost there. Right. Questions or things you want to look at?
So could you tell us
Yeah.
again about this indicator?
Yeah.
So it was clear.
Yes.
When you put indicator, it will be clear or it
Yep.
will be off?
No, it will stay clear until it gets all neutralized, and then it will turn pink.
Okay.
Oh, so I guess as long as we're down here, let's look at the lab for today, and then we'll have time to just get right into it when we get upstairs. Has anybody done this before? I think they also do it in physiology class or something with the dialysis bags, and you test if the stuff is coming out of the dialysis bag or not.
Read on bio.
In bio? Yeah, one of those classes they do it. So you may have done this before. But we talked about this in the last chapter where certain things will make it through these semi-permeable membranes and some won't. The semi-permeable membrane we're going to be using in this lab is called a dialysis membrane, and or a dialysis bag maybe. And it kind of just looks like, it's pretty weird if you haven't seen it, or it's a tube, but it just looks like a piece of plastic wrap. And you soak it in water, and then it becomes kind of like this jelly consistency, and then it turns into a tube that you can open up. And you're going to open up the tube, and then you got to tie the ends and make a little bag out of it. So there's a couple weird directions here that I want to go over. First of all, the whole idea of the lab is you're putting these 3 different things inside the bag. You're putting something, an ionic solution like salt, I think sodium chloride, glucose, so sugar, or sucrose maybe, and glucose, and starch, which is a colloid, a large molecule. You're putting all those in the membrane or in the bag. You're going to put the bag in some clean, fresh water, and then you're going to check to see what kind of stuff came out of the bag. So remember, in diffusion or dialysis, the particles will move to the area of lower concentration. So if there's a higher concentration of the stuff in the bag and a pure water on the outside of the bag, anything that can get through the membrane should go out into the solution surrounding the bag. Anything that's too big will get stuck in the bag. So that's the idea. You're going to do chemical tests for those different things. We can't see chloride ions. We can't see glucose molecules. We can't see starch molecules. So we need to do a chemical test to see if they're there or not. And that's what these different tests are. So you're going to look at the tests of something you know. So like you're going to take some sodium chloride. Obviously that contains chloride because sodium chloride. Then you're going to put some water in so you can see what it looks like positive, what it looks like negative. And then you're going to add some sodium or some silver nitrate to each. All right, and then you're going to write down your observations, like what did it do in pure water versus what did it do when you knew there was chloride there. So then later, you can test your solutions in the bag and in the surrounding stuff and see if there's chloride or not. Because you'll know what it looks like when there is chloride and what it looks like when there's no chloride based on the tests. There's a similar test for starch. You're going to look at this iodine reagent and see I think it turns blue or something like that. And then the glucose one is a little bit different in that you have to heat it. So you're going to put this Benedict's reagent in, which is a way to test for sugar. I think this is the one that turns blue. And then you're going to heat them in boiling water bath and see which one happens, or you know whether it's there or not based on the difference. Okay. The other weird direction here. So does that make sense about those tests? Now the other thing is, don't do that test first. You'll notice right at the very beginning, before you start the directions, it says do first and second above. Then do this. So don't start here. Go up to first and second. The reason for that is the first and second are things that need to kind of sit for a little while. So you do that first, get it sitting, and then you start doing those tests while you're waiting for it. If you don't do those first, then you're going to be behind on everything else because you got to go back and start over with that stuff. So you got to soak the membrane in the DI water for at least 15 minutes. And that's the thing that you're doing first. Then when you set it up, what you're going to do is, it says to cut about a 30 centimeter dialysis membrane, but you actually only are going to use half of it. So it doesn't matter if you cut it before or after soaking, but really you should use 2 15 centimeter dialysis membranes. The reason for that is that these things, once they soak, they're pretty breakable. They can rip pretty easily. So if you're tying it up and you rip it, you want to have one ready to go in case it gets screwed up. Otherwise, you got to wait 15 minutes again for a new one to soak in water. So soak 2 15 centimeter tubes or 1 30 centimeter tube in water. But if you soak it all together as a 30 centimeter tube, make sure you cut it in half before you actually use it, because you're only using half of it, a 15 centimeter section. Okay. We are going to secure it using an unknown method, because I'm not sure what we have up there. There's a couple of these methods here. This thing's a tube, so you just got to get the tube closed and sealed. One way to do that is roll it up and put bobby pins over the rolled up part. That'll seal it up. The other part, sometimes we have these little foam thingies that you kind of like fold it up and stick it in the foam thingy. I'm not sure what we have up there. We might also just have some thread. That works too. You just fold it over and you tie a couple knots around it, and that holds it tight. The point is just to make sure that it can actually hold water. So once you get it sealed, put some DI water in the bag and then just see if it's actually holding it or if it's coming out. Because if it's leaking out of the bag, the experiment's not going to work and you have to start over. All right. Once you pour it out, then you can put your actual solution in there and seal it up, check it to make sure it doesn't leak once both sides are sealed, and then you're going to put it in the DI water. You're going to take samples at 0, 20, and 40 minutes. So keep a stopwatch going, and you're going to take some samples of the solution around the dialysis bag. Now this is the outer solution because we want to know what has come out into the outer solution, not in the bag. We're not opening the bag after 20 minutes. Leave the bag closed, pour off some of the solution that was around it, and see if some of the stuff has come out yet. And so you're going to check that at 0, 20, and 40 minutes, and then test for chloride, glucose, and starch for each of those samples and write down whether or not they have chloride, glucose, and starch. Then at the very end, you're going to open up the bag after 40 minutes. You're going to open up the bag and test what's actually inside the bag. So you're going to see if there's any chloride left, if there's any glucose left, and if there's any starch left actually inside the bag. Are there any questions about that procedure? Or that what we're going to do there? Okay.
So how can we see at the end of the bag?
You're going to open the bag
Okay.
and pour a sample out and test it, or 3 samples out and test it using those 3 tests. Excuse me. At some point in this downtime also, you can work on the filtration. So while you're waiting those 0, 20, 40 minute part, you can work on part C, which you're going to look at the same mixture that you started with, and you're going to filter it through this powdered charcoal and see if anything comes out through the filter. So you analyze the filtrate with those same 3 tests for chloride, starch, and glucose. So you're going to do those 3 tests a bunch of times. All right, and you can do that at some point. The other thing we need to do is carve a pumpkin so that we can blow it up. The way the thing works, we had one last week. We blew it up a couple times. It worked pretty well, but it finally broke, so we have to make a new pumpkin. The way that this thing works, it's pretty cool. We carve the pumpkin, like make a face on it, and then we put the stuff inside that forms acetylene gas, which is a flammable gas that's used in welding. Let it build up in the pumpkin, and then light it. And then it blows all the pieces out, like you put the pieces back in the eye and nose and mouth and stuff. The way we find it works best, so whoever has some good artistic pumpkin skills here, if you draw a face on the pumpkin, you just want something that is not intricate. You want like big triangle eyes and a triangle nose and like a big mouth or something, because you don't want the pieces to get stuck in there. You want them to blow out nice and easily. So whoever wants to work on the pumpkin when you have some downtime, we'll have that out in the lab too. Maybe I'll get it all cleaned out while you get everything set up, and then somebody can carve the face, and then we'll blow it up at the end. All right, questions about the lab? Questions about stuff? So it's 1:30 now. I will see if we can get in the room like 15 minutes early to get started. So we'll plan on getting started about 1:45. If there's still a class in there, we'll have to wait, but I'll be over there to check it out.